Hi, everybody, and welcome to this episode of Google Hangouts with Sigma Xi's distinguished lecturers. I'm Fenella Saunders. I'm the managing editor of American Scientist magazine. And this particular episode of our Google Hangouts is sponsored by the RTP chapter of Sigma Xi. So hello to all the members in those chapters and to other Sigma Xi members who are watching. And welcome to anybody else who's watching as well. So in this talk, we will have the ability to have people ask questions. You should see a chat window on the right side of your screen. You can submit questions during the talk and we'll ask the speaker to answer them. If you're a Sigma Xi member and you have follow-up questions, you can go to Sigma Xi's online communities page, the lab, and submit your questions there, and we'll ask Dr. Foster to answer them. So today, we're very excited to have Dr. Krishna Foster, who is a chemist at California State University, Los Angeles, and she is going to be talking to us about particulate matter, the role of sunlight and how the chemical composition of that matter changes, and its effect on air pollution. So thank you so much for joining us, Dr. Foster.
I'm happy to be here.
Great, thank you so much. Okay, so first of all, I thought we might start off with a little bit of a basic introduction for people who might not be as familiar. I wonder if we could talk about particulates and sort of what they are and what they're composed of.
Sure, of course. Particulates are compounds that are in the air. They're not gaseous. They are either made out of solids and liquids. And that's what makes them different than the rest of the atmosphere. They're suspended in air, and they can last there for sometimes days or weeks. This all depends on their size. So you think about basic things that you can see, like dust. This is a huge piece of particulate matter, is the actual dust that you see with your naked eye. This is larger than 10 microns. Micron is the measure, where a few microns is about the width of a hair. Tens of microns make up the width of a hair. So 10 microns are greater. Those are all generated through mechanical motion. So the sea water hitting the beach, or the kicking up dust. That's one class. And we aren't so concerned about that anymore because it doesn't get too deep into our respiratory systems, into our bodies. The current research is looking at particles that are smaller than 2.5 microns in diameter. So that's 1/4 of a piece of dust. It's only 1/4 as big. And because of that, when you simply do something as basic as inhale, you can then bring these little particles into your body. And so it becomes an issue of health concern when you're talking about the very fine particles. So that's one aspect. Also remember where they are. So they're in the atmosphere. That means they're part of the atmospheric chemistry. And the types of reactions that happen on particles may be the same exact ones that happen in the gas phase. That is, the reactants are the same. But the outcome, how long it will take for a chemical change, or even what the products will be, that's completely different. So I study the reaction of compounds in the atmosphere on particulate matter because this makes a difference as far as how that initial pollutant will change over time.
Okay, so can we also just, you mentioned some of the size range here, but just how small do these particulates get? You mentioned sort of the maximum maybe size, but do they get smaller than that?
Oh, absolutely. Absolutely. So when I talked about the mechanically generated ones being 10 microns or bigger, when we get down to 2.5, this is the maximum cutoff for what you would expect for something that's chemically generated. So that means it may have even started out in the gas phase, but over time it takes up water and it builds into a particle, a small one. And you have the progression of this area of research has gone from 10 down to 2.5. Now we have research on particles less than 1 micron in diameter, and this is a hot area of research too. The smaller they get, they are to be part of your own biology, and therefore the significance of this area of research goes up. So part of our limit is our ability to detect small particles and distinguish them by size. There are methods out there, but they're not widely disseminated. So without commercially, you can look at 10 microns or greater, 2.5 microns or greater. But the question was, are there smaller particles? Absolutely. And they do matter, and people are researching them. But it's more of an active area of research on how to measure them. It's not something that you can do by buying something off the shelf.
Right, okay, that makes a lot of sense. Now you mentioned a few mechanisms by which these particulates are created, from chemical reactions all the way up to kind of like mechanical ones. Is there a wider range of reactions that can produce these particulates, or is that kind of the range that we're talking about?
Is there a wider range of
I mean, are there other mechanisms by which these particulates can be formed?
Absolutely. These are the two major areas, either mechanical or chemical generated. And the chemical generation, there's several subcategories of that. It can be something that starts from a gas phase and grows over time, or it can be a particle exists and then it takes up chemicals, say, for example, a water droplet.
So water even can be the basis for the formation of some of these particulates.
Yes, when you talk about something as basic as water, water is part of the system. But if you've ever made a salad, you know that oil and water repel each other. So you have multiple compounds on a particle, and you're going to find that the water will congregate towards the middle with its strong forces, and there's an oily outer layer on some particles. And so water is often a significant factor. We need to know how strong the attractive forces are of a particle to water, because that changes its composition over time. So water is absolutely an important ingredient.
So are we able to sense these particulates just with our regular senses, or is this something you need equipment to see?
This is something you need equipment to see. You need equipment to see the very small ones. We're familiar with dust, right? We try to get rid of it. But the small ones, no, you can't see them with the naked eye.
Right. But I think that for the larger ones you're talking about, maybe they're not health concerns, but just to give people sort of a sense of familiarity. I mean, our sense of smell, for instance, I think can take up pretty small particles and detect things at pretty high sensitivities. Is that something, can we smell a lot of these particles? Is that a lot where scents come from?
You have your sense, the nose is a great sensory organ. And for most compounds that do have scent, you can have one particle in a million total particles. So that's what you're experiencing, 1 in a million, and your nose can sense that. And so this is easily done with the gas phase particles, but you can also see, even with fairly large mechanical particles, you can see that when you smell, you're at the beach, right? I'm not saying that this is 100% particulate matter, but it's certainly associated with that being part of the atmosphere too. So you can smell if you're at the beach or not. You can smell if there's automobile exhaust or not. And these are mixtures of both gases and particles.
Right, okay. And is this the case where the particles themselves might not be necessarily good or necessarily bad? It might just be more of a quantity effect, or are there some that even in very low quantities could be particularly dangerous or harmful?
So I can answer that from my perspective, which is a chemist studying these systems. So for a deeper understanding, we need a toxicologist or somebody in the medical profession. However, I will tell you what I do know about these systems is that it does matter particles are not necessarily good or bad from the outset. That you don't just look at a particle and say, oh, that's bad. You can have exposure. We were just talking about water, and you can die of drinking too much water. It's hard to do, but it happens. So that's an example of a chemical compound that we need as part of our life in large quantities, but too much of even a good thing can be detrimental. And so when I talk about air pollution, this is nothing that was naturally intended to be there. It's nothing that is necessary for our vitality. So rarely do we look at something categorized as an air pollutant and say it's just good under all circumstances. When it comes to exposure to air pollution, though, duration and also just that initial intensity, how much is there and how long are you exposed to it? Both of those are factors that can affect human health. And one place to look at this is government websites. For example, I'm in California, so the Air Quality Management District posts on a regular basis the it's a health index score. So there's a health now I want to know the number. It's an index. And what it does is it categorizes how potentially harmful this exposure is to your health. So that is categorized then by populations. You have sensitive populations, and they need a smaller exposure to pollutants in order to be harmed. And then you have the average citizen, and then you have people who can endure most anything. So in short, just duration and intensity matter. And these values are charted for us for 8 of the most well-watched pollutants by government agencies.
Right, okay. And is it possible for you to give us a little sense of the history of this field? How long have people been studying particulates in relation to air quality?
Absolutely. Well, air quality history is actually a really intriguing thing. I use it with my students to let them know how science happens. You know, often you have explosions in science because there is a real pressing need. So in Los Angeles, for example, we had in the 1940s all these episodes where crazy things were happening. You put out your clothes to dry and they come back in smelling odd. You are walking down the street and your eyes start tearing up and it's hard to breathe. And people had a hard time finding out what was the reason for this. And so from the very beginning of a research study, you think about all possible things. You not only are the clothes not smelling well, but they might even look dirty. So the particles were there from the beginning of studies of the type of air pollution we have in Los Angeles. The field really, I would call the 1940s is where it began. But then, in this case, the gas-phase pollutants were the ones causing the most harm. So then, you know, we're kind of like scientists follow trends. We're innovative, absolutely. But if there's a topic that people are talking about, hundreds of people will go study that same topic. And so there was a lot of discussion about the gas phase, and it sat there for a good, I would say until about the 1980s, really. About 40 years, most of atmospheric chemistry was focused on gas phase. And then what happened? We had the stratospheric ozone hole. And so in the 1980s, this was really the onset of a surge of research in particulate matter and its role in atmospheric chemistry. So to explain that story, and it was impactful for me because I was just deciding what to do about graduate school and where to study. And so with this, my dissertation is in this area. So I started in the 80s, well, 90s, something, late 80s, early 90s. Right. Mm-hmm. I started my work with particulate matter, and that was really the start of an explosion. I'm not the first, I won't be the last, but it was a surge because they could not explain with gas phase chemistry alone how you could see massive and rapid reductions in stratospheric ozone. Somebody came up with the idea, what about those transient clouds that tend to form at the same time we see ozone depletion? And so that was really the beginning, is that we learned that the halogens, chlorine is an example of the halogens, that were involved with stratospheric ozone depletion were activated. They were made photochemically available. That means they were made available for activation from sunlight, okay? Only when you had these clouds present. Otherwise, it would stay unavailable. It would be there, but in compounds that could not be release the chlorine. And this is what you need. Chlorine radicals destroy ozone. And so, so yes, it's a fairly new area of research, and it's come down over time. So I'm talking about the stratosphere, and that is, depending on where you are on the globe, it certainly has nothing to do with our weather systems. It has minimal to do with what we do as far as emitting pollutions here at surface level. At the poles, for example, it's about 15 kilometers high is the lowest part of the stratosphere. So after you get to our area, our layer, that's called the troposphere, which is below that, they're chemically isolated. And it took a long time. We sat in the 80s and looked at stratospheric ozone. I think it took another 20 years before we really started to engage in processes associated with chemical change involving particulate matter at the Earth's surface. And the reason for that is it's complex. It's very complex compared to gas phases.
Okay. But one thing we haven't mentioned as a source of these particulates is combustion, and you had mentioned exhaust from cars, but can you talk about particulates that come out of combustion and sort of what those are? And some of those are particularly damaging, I think.
Absolutely, I can talk about that. When we talk about combustion processes, the first one you might think of is soot. And actually, I want to supplement something I said already. We had the role of soot in the 1800s. In London, you had a job where young boys would crawl up chimneys to clean them out, a chimney sweep. And they were getting astronomical rates of cancer as they grew up. And so we're saying, what is it about the chimney sweep and their labor that causes them to become ill? And so this is the beginning of automobile exhaust is what we're talking about in the modern age, but it's the similar composition to anything you would get from incomplete combustion processes. So whether you're burning wood or whether you're burning gasoline, you talk to your high school chemistry teacher and they will tell you your fuel converts to CO2, carbon dioxide, and water. That's only part of the story. Yes, it's most likely that those will be the products, but anytime you burn a fuel, you're going to have the possibility of creating other compounds, and some of those are toxic. So the compound formed in incomplete combustion, whether it's the chimney sweeps in 1800s or the automobiles and trucks on the roads today, you create a compound that I will call for short PAH. That stands for polycyclic aromatic hydrocarbons. And if there are any chemists out there, these are simply a series of benzene rings that are tied together to form different structures. And
right, and just so for people who don't know what a benzene ring is, it's a 6-carbon sort of stop-shine hexagon-shaped ring. Is that right?
Absolutely. It looks just like a little hexagon, and then they draw the conjugate pi bonds. They have electrons all over. It's very pretty. It's very symmetric. It's a hexagon shape with lines on every other space.
Right, and so in case people are interested in learning more, we actually had a perspective column from Roald Hoffman on benzene rings not too long ago, if you want to look that up. So.
Oh, wonderful. And what it is about these benzene rings is many of the molecules that are part of our life processes have similar structures. And one of the routes of toxicity is just confusion. You have a compound that is so similar to something your body needs to function that when the foreign compound is ingested, it causes harm. So the PAH, which is made of benzene rings, was a problem for the chimney sweeps. It is now known to be carcinogenic and mutagenic, and it's also ubiquitous. You find it everywhere. So I don't want to scare anybody because we just talked about how can hurt you. And so exposure to some PAH is natural. It happens in barbecues. That's definitely an incomplete combustion, and our bodies are very good at protecting themselves. But chronic exposure, intense exposure, these become problematic. And so we're back to an earlier question, is what happens with a chemical? Is it good or bad? You know, I love a good piece of barbecued corn.
Right.
Barbecue salmon. I love barbecue, and I will eat my PAH comfortably with a smile. So minimal exposure is not a problem, but I choose not to live right off a congested highway. That's a different thing. That chronic exposure to particulate matter is something I choose not to do. So the PAH is something that we track. I track in my research. Other compounds on particles involve heavy metals. Same story. Small exposure to heavy metals is not a problem, but I don't think I have to go in much detail if I say words like mercury or lead exposure, because too much exposure, especially to sensitive groups, the very young, they watch children under 2 for exposure, especially to lead. Because too much exposure to heavy metals can certainly deal with your neurological functions and be detrimental to those systems permanently. So heavy metals also find themselves onto particulate matter that's created through automobile exhaust. Heavy metals and PAH are the 2 classes that we watch very carefully when we study air quality.
Right, okay. So I think you've been kind of alluding to this, but just to be a little more specific, these substances, these particulates, they're not really inert, they're reactive. Is that correct?
Oh, absolutely. They are reactive, and this is something we talk about, chronological changes in research. They're reactive, and the initial thing was to just characterize the emissions. So several years ago, people would work to characterize exactly what are the chemical compounds on the particles. Now that we have a good handle on that, the issue is what happens as they transform. This hits home because when I was starting this research project, I was simply looking at the role of interfaces in changing the degradation of PAH. That means how quickly are they removed from the environment? Can you tell me about something, the pathway a compound will take from the time it's admitted until it's removed? And I was obsessing over the removal of benzoapyrene. When I began that course of research, I quickly learned that the product produced in the presence of oxygen, and I use laboratory irradiation, but you could substitute solar irradiation. The product was also active with respects to those same things. So needless to say, that study stopped pretty quick because you can't do a kinetic study without having a stable product.
So you just said benzoapyrene. Is that one of these PAHs that you were talking about?
Absolutely. BAP, or benzoapyrene, is a PAH.
Okay, sorry to interrupt, but go ahead.
No problem. So what do is one of the things you do as science is you're resilient, and your job is to identify and explore research questions. And so when you have an experiment that doesn't go as planned, you learn over time to embrace that. And it's going to change the timeline of coming to conclusion, but at the same time, it can open up new areas of research. So when I was not able to study the degradation of benzoapyrene, BAP, a type of PAH, I switched gears and went on to study the product of this reaction, which is benzoapyrene dione. So it's reacted with oxygen, and it has oxygen groups onto that parent structure. And so I just did an about face and started studying the photochemistry of the product, because it was greatly misunderstood when I started this course of work.
Right, okay. So it sounds like you may in the atmosphere be looking at things that are in various stages of degradation, multiple products. Is it a question as much of the mix in terms of the reactions that you're getting, the mix of compounds that are there and the mix of reactants?
Absolutely. The mix, or when you're looking at proposed chemical reactions, um, you're not just looking at a single compound, but what is in that mixture, what's around it, makes all the difference in the world. We can talk about basic things like how you take a PAH and you have it disappear from the atmosphere. How quickly it disappears depends on if that particle is soot or if it is dust, or if that particle contains water or is water-free. All of these are variables, and so what else is happening in that microenvironment is everything as far as how a chemical reaction will proceed in the real world. One of the advantages of doing laboratory science and even computational modeling of those results is we can reduce the variables. And we can say, oh, what is the role of just water? What is the role of soot versus a surrogate for dust, which would be silicon oxide? And you can change the surface. Quartz would be one way to go. So you can control as many variables as possible to try to answer a small question related to a bigger question. Because the mixture, the environment where the chemical change is happening is everything. Everything.
Right. I was going to ask you at some point about your laboratory work, but since we're talking about that now, is it kind of the do you have the ability to sort of add back in variables one at a time so you can kind of figure out what they each do in isolation as well as in groups?
Absolutely. So we can control our systems, and our job is to try to mimic what's happening in the actual atmosphere to the best of our ability. But we can do that one variable at a time. For example, if I'm getting ready to do measurements of PAH in the atmosphere, we have one course of study ready to do that. I will prepare with the detection techniques. So we start by optimizing our detection techniques for just 1 out of 16. There are 16 that the Environmental Protection Agency are tracing. They say these are priority pollutants and we need to know where they are. So I will develop my detection techniques based on one, and after that's clear, I can expand to more of them. And if I want to look at a chemical transformation, the same thing. So I have one experiment where we're looking at a reaction in solution, which is easier to understand than a reaction on an interface. And then we use everything we've learned about the simplified system to scale up and make it more and more complicated. One of the advantages I have in my research, and you'll find if you talk to different scientists, is that the description plays well with others, is becoming more important as far as a job quality. And that collaborative research allows us to advance even faster in addressing different questions than working alone. And so you do what you do well, you do it in groups. My group is made out of graduate students and undergraduate students, and I collaborate with faculty inside and outside of my department at Cal State LA. I also work with faculty who do things different than myself. You look for people who are complement your research, but are looking at it a totally different way. Because diversity in thought is the quickest way to a solution that's significant and innovative. And so I do my laboratory work, and I produce physical constants that are then used by my modeler, who can do that upscaling a lot quicker than I can. Here's a very clean system, and I can tell you how PAH is operating in this environment. Now let's use that and make some assumptions about how it would react in the actual environment. And instead of trying to do that experimentally, you could do more experimental approaches to begin to answer that, or you can do it computationally. So my results are put into a model by my collaborator at UC Irvine, Donald Dabdub. And here he has a three-dimensional model that's the entire surface and then also with altitude, looking at air quality and transformations over time in the Los Angeles air basin. So I put in my very simplified systems and we put them into this model, and it still doesn't represent 100% what's happening in the real world because mixtures do matter. Microenvironments make all the difference. But what it does do effectively is it allows us to scale up. It allows us to scale up and make predictions and begin to add enlightenment to different systems that we could never do one person at a time, one lab at a time, or one experiment at a time.
So you feel that the cross-disciplinary nature of your field is pretty strong? Are you there, Dr. Foster?
I am here. I lost you for just a minute.
Sorry.
Question.
The question was, you feel that the cross-disciplinary nature of your field is pretty strong?
The cross-disciplinary nature of my field is very strong. I've worked in different communities. My dissertation training was interdisciplinary. I'm hired here as a physical chemist. My work is applied to atmospheric systems, and I have training in surface science. And all three communities, professional communities, operate differently, interact differently. One of the things I like about the atmospheric chemistry community is you're dealing with a community that is based on solving social problems that are immediate. You're dealing with very complex problems where it's humbling as a scientist in that community. It's foolish to think that you can do the work by yourself. And this field is newer than many of the other areas of science. So with that newness comes, I said, atmospheric chemistry, as far as particulate matter, blossomed in the 80s. And by that time, things were shifting as far as the workforce, as far as who is a scientist and what makes somebody a scientist and who's welcome to participate. So atmospheric chemistry has more women, for example, than physical chemistry for certain. And it always has. There's no history of having women marginalized in that discipline. Mm-hmm. Because it's always been, it was created with a with gender diversity from the onset. And so it is an open and collaborative environment for multiple reasons. First of all, when did it explode historically, chronologically, what was happening in the workforce? And then also because of the nature and urgency of the problems. You have to be open, you have to be humble, you have to accept, you have to be expert in what you do, but also accept and trust that other people will do their part to address these burning questions.
Right, that makes sense. Can we switch gears a little bit for a second? I wanted to go back and talk more about some of the health effects. And you had mentioned the possibility for carcinogenic effects with some of these pollutants, but I think air quality has sort of less direct effects on health as well. I wondered if you could talk about those sorts of effects and the impact that it has on human health.
So yes, I go straight for the big guns, the deathly mortality issues of air quality. There's also just basic inconvenience. One of the reasons I became interested is because when I was in high school, I was a competitive runner. I did cross country and track. And just as a regular citizen, not even as a scientist, you can see the impacts on your respiratory system. If you are an athlete outside, like a whole lot of people probably even listening, if you've ever experienced this lifestyle, you know that when you're trying to breathe hard, everything counts, including the quality of the air. And some days, no matter what you did, your nose would start burning. You know, you couldn't get that time or that power that you were trained for because of your fuel. Your air quality was not where it should be. And so this is indeed a variable that makes a big difference.
So does it have an impact on things like asthma and other kind of chronic conditions?
Sure, sure. So I went for the very light. That's a choice. If you want to breathe hard, if you choose to be athletic, that's a choice. But everyone needs to breathe. And air quality is known to have immediate effects. It's problematic for sensitive populations, which includes those who are asthmatic. Anybody with a respiratory problem is sensitive to the quality of the air. I live in Southern California, so there are people with the ability to change neighborhoods. When they do have an asthmatic child, for example, they will pack up and move to get better air quality for the health and comfort of that child. So asthma is one of the big ones. Back to the mortality issues, is cardiovascular health is also impacted by air quality. When we talk about sensitive populations, of course, you think about the elderly and the young, but also how well a fetus developed is another issue. An active area of research is what's happening before folks are on Earth. I don't know how to say this. I need to get away from it. But the
Right.
issue is that we have the unborn affected disproportionately by exposure to air quality. So just a pregnant woman needs to be sensitive to her inhalation. And as asthma is probably the biggest impact because it's so immediate. Yes.
Right, okay. So one of the things that you mentioned before, I wanted to see if we could get into a little bit more of the mechanism, is the factor of the environment of itself, the sun, having a role here in affecting these particulates. I wondered if you could talk about how the sun actually reacts with these particles and what is causing that reaction.
So the role of the sun, I'd love to talk about that, is we think about it just colloquially as the biggest energy source. There wouldn't be all this discussion about solar panels and capturing the energy of the sun. So I'll start there because I feel many can relate to that. It's the greatest energy source. It's primary energy source because chemical energy that we use as gasoline and other petroleum fuels, it started from the sun. It's just that the plants are able to capture it effectively. And so plants will harvest the sun's energy and create the fuels that we use day to day, sometimes over billions of years. It depends on which fuel you're using. So the sun is a powerful source of energy. We start there. When it comes to chemical behavior and chemical transformation, if you're early in your studies, you'll soon know, or you have learned, that the electron is everything. And what these electrons are doing as a subatomic particle, where they are and what they're exposed to, influences how the compound will react. What happens in a chemical compound in the presence of sun is you have electrons minding their own business. They're doing whatever they would as if the sun were not there. And then they're exposed to this energy source. And if it's the right type of energy, the right wavelength of energy, the compound will absorb it and it goes into the particle. This causes the electrons to be excited. And once that happens, the world is open as far as how that chemical will respond. So photochemistry means that the light and its ability to excite the electrons is an important factor in making that chemical transformation take place. So we've talked about the energy getting into the particle, and the energy is stored where the electrons move stepwise. It's quantum chemistry, it's quantized. So the electrons were at, say, stage 1. Then they absorb the right type of energy and they live at stage 2. But they really want to go back to stage 1. So the way it releases that extra energy could be simply it releases more light. It can let the energy go as light radiation, or it can transfer that energy to someone else. So I guess a social example is if the party is dead and everyone's just kind of sitting around, and then somebody comes in and they're just bubbling with joy. then the party wakes up. That person collides with the next one, collides with the next one, and all of a sudden everyone's having a great time because the particles are doing the same thing. You have one particle has now absorbed this energy. It's excited, and it's not actually going to stay there like at a party. It'll just transfer it to another molecule. And then that molecule will either transfer it to something else or transform.
Right,
So
okay.
that's the role of sunlight.
Sorry. Okay, so the sun is basically kind of just adding the energy to the reaction to make the particles more reactive. Is that a good way to put it?
Yes.
Right, okay. So one of the things in your research you talk about is when the sun has interacted with these particles, it kind of ages them. I wondered if you could sort of define that for people who might not be familiar with that characterization of these particles.
Sure. So if we go back to the initial admission, you think about morning rush hour, for example. Not all of you live in LA, so you don't understand what I know as far as the intensity of morning rush hour. You have a congestion of cars, and they're all sitting there burning their fossil fuels and emitting air pollutions. That's stage one. That's time zero. You have emissions, and those are fairly well characterized, what they look like when they come straight out of a tailpipe. But when I go back to the small particles, the PM 2.5 and lower, they don't necessarily settle down to the ground instantly. Certainly, it takes them a while, not only hours, but in some cases days for the 2.5, and in some cases several days, on the order of weeks. These particles can stay in the atmosphere, and therefore they have time to react with the sunlight. So you started out with an initial pollutant that was well characterized, but now we have the sun, which is an endless source of energy. It's moving the electrons around in those pollutants that were originally emitted, and they're now in a position to change over time. You also have the power of a mixture where the PAH is not going to change all by itself. It will react with something else. And there are several oxidants that react with PAH. I'm just using this as an example of one type of pollutant. So you're exposed to sunlight, you're exposed to oxidants, and time passes. So that means what you had at time zero when you had the tailpipe is different than what you're going to have 5 days later, because it's changing from the minute it enters the atmosphere.
Right, okay. And is it sort of, I think one of the things you're working on, but I gather it's not very well characterized, what these will react to become? Is there sort of a random distribution of products they can turn into based on the mix and things like that, or is that well characterized?
We're learning. This is an active area of research. So the particular problem that I'm interested in is actually what is the interaction between the PAH, O2, molecular oxygen, which is one of the most passive oxidants there are, and sunlight. So when these three things come together, you can take the passive little simple molecular oxygen, and here's the sequence. Let me back up a little bit. You have the pH that's been emitted. That can either be a fresh one that was just emitted from the tailpipe, or it can be something related to that, something that has changed over time. We're now 5 days later. Mm-hmm. Both of them engage in the same course of chemistry. The PAH, or its photoproduct, the derivative, absorbs sunlight very readily, and we know this. It has strong absorption in the ultraviolet region present at the Earth's surface. So it takes the sunlight. It takes the sunlight into its electronic structure, producing electronically excited PAH. And so it's ready for anything. It's ready to go. One of the things that it can do is just pass that energy back to oxygen. So then you have ground state molecular oxygen becomes excited state molecular oxygen. And that is then not just a plain oxidant, but a superoxidant. a reactive oxygen species. So here we have an example of where the pollutant, whether it's fresh or aged on particulate matter, is affecting the chemistry around it. It's changing the oxidation capacity in that system. So the oxidation power of singlet molecular oxygen is so much more intense than ground state oxygen that this is why I study what do I do. What is the importance of oxidation? Oxidation is not good or bad, but it induces change. It induces change, and if we want to understand air quality, we have to understand and characterize the different oxidants in our atmospheric systems. This includes those found and generated on particulate matter.
Right, okay. And so I gather that it can kind of almost be a chain of reactions that you're getting on here. You're not talking about just one reaction and it stops. It can have these multiple stages. It seems like a very complex system.
Yes, yes, and this is something that the audience can do. If you just Google air pollution, you're going to find very quickly how complex it really is. So we talk about one series of reactions. When I say PAH absorbs sunlight energy and forms singlet molecular oxygen, I'm already talking about at least a dozen reactions. Okay, so there's several different steps in this mechanism for this type of chemical transformation. And then when you put it all together and you think of the different chemical compounds in the system, it becomes very complex. Let me put this in perspective. When I took my recent data and I put it into the air quality model, that model had over 300 reactions. And then we added 3 or 4 more on top of that. So 300 just to get started, right? Just to explain a couple of the transformations, not all of them, but ozone formation and secondary organic aerosol. These are the things we were looking at this time. You need at least 300 reactions to even start the conversation.
Right, okay. And so one of the things I wondered is the singlet molecular oxygen that you're talking about, does that relate to free radicals? I think that's a term that people hear bandied about.
Mm-hmm. It relates to free radicals, and that free radicals are another type of oxidant. So early in my career, I looked for gaseous molecular bromine, and we're interested in that particular oxidant because it reacts with sunlight, and instead of just transferring energy, it actually breaks the bromide-bromide bond. And these free radicals are important oxidants that are characterized along with other oxidants in atmospheric systems. The big one in urban environments are the nitrogen oxides. We need to know where those are and what their concentrations are. They're generated in high temperature combustion processes. So they're generated along with the PAH. They're generated simultaneously in combustion of fossil fuels.
Right, okay. And so when you were talking before about some of your lab studies and your abilities to kind of tease out some of these reactions, I was just wondering, you're talking about putting those into the models. Have these recent studies kind of changed the perception of how these particulates react within these systems?
Well, for me, yes. What we have is a ship that moves very slowly. I'm currently talking about an article that is in review. You know, it's at the beginning of the process, and so this research will mature over time. Other people are engaged in the same course of studies, but you can have a few people shouting from the rooftops. It takes hundreds of people working and believing each other to have a shift in the way things function. And so science requires innovation. It requires people to work independently and collaboratively. And then also, we are skeptics by our nature. We're trained to be skeptical. So it takes a lot of publications, a lot of information before the paradigm will shift. And that's part of the thing. You just do your part. You're not responsible for the whole shift. You just have an interesting idea, you explore it, and that's the main purpose of practicing science, is to be a conscientious explorer, to ask meaningful research questions and dive into them. And we're not responsible for the outcomes. We're ethical, of course. There's an ethics question there, but we can't make the whole community shift with just one study.
Right, of course. So a little while ago in our computing science column, one of our columnists kind of, as he put it, popped the hood on some of these climate models to try to see how they work. And obviously they're extremely complex. As somebody who's kind of involved, at least in some sense, in the back end of these climate models, I wondered if you could talk about sort of some of the perception of these models that is in the public. Some people are dismissive, unfortunately, and ways that we might sort of give people a better appreciation for just what goes into these models and how much data is really involved.
I think that's an excellent question, in that global climate change is one of the most important issues of our generation, because this is basically our last chance to do anything about it. If we don't, it becomes a runaway train, and we live with regrets as long as we live. So the issue is, how do you make policy decisions based on scientific results? And I think the biggest misunderstanding is how science works, how scientists function, what we do and what we don't do. We explore, we create knowledge, and we don't decide what happens with that knowledge. When you talk about what's happening in the global climate change community, it's not just one marginalized scientist. You're talking about the vast majority of practitioners believing wholeheartedly that this is taking place. What we can't do is say that science ever stops, because we're always discovering. We're always discovering at the same time. But when you have consensus built to the degree that it's been built around global climate change, I believe it's foolish not to take that seriously. With this particular one, we have time sensitive. It's a time sensitive problem. And so if we don't create policy preventive purposes, then the consequences could be dire. I can go back to the 80s and talk about how this worked. I'm talking about polar stratospheric change, where you have ozone depletion in the polar regions. People call it the ozone hole. And so the scientists were very forthcoming with the politicians, the legislators, who have to decide what to do with this information about what they had discovered. There was a kind of urgency to present what they were coming onto consensus to as far as the source of this problem. It ended up in strict legislation against the use of CFCs, chlorofluorocarbons. But you talk about the value of collaboration. As a scientist, I take full responsibility for discovering research questions, coming to conclusion, and sharing those results. That's what I do. And then I choose to share those results broadly because I believe in the significance of that question and the greater good. It's happening now again in the scientific community, where scientists are screaming at the top of their lungs, would you listen to me? But it takes a collaboration. The legislation, which is driven by the people, right? They are representations of each of us. The legislation is slower to move because there are economic consequences. There's always a yin and a yang, a give and a take. It's not a simple way. It's not a simple problem to legislate because of our dependence on fossil fuels. But at the same time, the science has come to consensus. And I cannot say as a scientist that it's concluded, because that's not what we do. We never wholeheartedly conclude anything. We're always adding to the existing knowledge a new piece of information and consensus has been clearly established in the scientific community. And now it's time for collaboration with the legislators.
Right, okay. Well, let's hope there's some movement in that area. I do want to just quickly, because we're getting a little close to the end of our time, I don't want to give people the impression that you're entirely a lab scientist, because you do some field work as well, particularly in the Arctic. And I wondered if you could talk about what you were studying there.
Sure. So I was still studying particulate matter, but I did some work at UC Irvine during my postdoctoral years with Barbara Finlayson-Pitts. And what we did here was amazing. As scientists, you have the opportunity to do things and discover things that people who have different professions don't. So scientists and military personnel are the only folks able to go to Alert Nunavut, Canada. This is the northernmost land location in the entire world. And so it was established as a surveillance unit of the military during the Cold War. But the site has now transformed to, of course, military personnel, but at times half the visitors at the site in Alert are scientists. And it's because here we can study particulate matter, yes, but without the interference of urban systems, human pollutants is much more controlled. Some pollutants will travel to the Arctic and other remote places, but the system is so pristine that we can just answer questions we couldn't otherwise. It also has no sunlight for several weeks at a time. So if you're dealing with light-sensitive chemistry, it makes sense to go somewhere where you have lights off, lights on. And so we studied those transformations, and we learned, to make a long story short, that you had particulate matter, the mechanical kind, just sea salt, would react. My first research project here was to discover the oxidant that took bromide, Br-. This is akin to Cl-, part of sodium chloride, which you all eat, right? So it's not a big deal. You'll find a little bromide in your sea salt, a very passive, inert compound. But under the right circumstances, it can produce Br2, which reacts with light, gives us free radicals. Free radicals are powerful oxidants and change the quality of the air.
That's really interesting. So I do have to wonder, though, if there could be anthropogenic factors involved in what you're seeing in the Arctic, because there's so much about, for instance, melting sea ice happening in that area, and I'm wondering if that's affecting the particulates that you're getting there.
There are variables. I don't know if surface temperature is the most important, but you do have pollutants that travel over time. We were measuring fluctuations in the nitrogen oxide species, and oxidation by nitrogen oxides absorbed in the snow is one of the potential oxidants. So no, it's one world, and there's nowhere that's completely removed from the things we do as humans.
Right, okay. We've only got a couple of minutes. I wanted to just answer a question from the audience, basically asking, they're admiring your Theodore Gray poster, by the way, behind you. We've had reviews of his books in the magazine before, but they're wondering if you had some favorite books on chemistry or science generally to recommend for non-chemists.
Oh, wow. I read so many technical books, that's a hard question. I can tell you my favorite physical chemistry book, which is McQuarrie and Simon, A Molecular Approach.
Right.
I love it. As far as books for non-scientists, I'm looking at my shelf, The Immortal Life of Henrietta Lacks.
Right, yeah, that's a great one.
I would recommend that one because it's both social and scientific. I told my students one day to go out for extra credit and report on contagion. I'm talking about media that's accessible to the general public, that gives you an idea for what we do as scientists and the decisions we have to make. There are many places to learn about science, but there are some fun ways to get that information on the lifestyle that we lead.
Right. That's great. So just as a wrap-up question, I mean, one of the things that I wondered if you might have a little advice for people who are kind of starting out either as early career scientists or even as students who want to get into a field that has a lot of large, complex problems. If you had any advice for them on ways to kind of handle getting into that field and how they might specialize and still feel like they're having an impact.
Absolutely. I would say there's some academic skills and some life skills that are important to put in place as soon as possible. Academically, I was talking to my colleague about how we're the lucky ones because there's not a single academic skill set that goes unused. In science, you have to write just as well as you handle numbers, just as well as you look at the big problem and plan experiments. The science methodology is just part of that. So academically, do your math, do your writing, and don't ignore anything. Personally, just extend yourself. You know, nurture the curiosity, never stop asking questions. And this is, if you have any 3-year-olds in your life,
Which
nieces,
I do.
nephews, daughters, right? You understand that sometimes you want to stop them from asking questions, but you have to resist against that and realize that the question is the foundation of scientific discovery. So encourage questions in yourself and others.
Great. Okay. Well, we're out of time, so unfortunately we're going to have to leave it there, but really great discussion. Thank you so much for participating in this Google Hangout with us, and we really appreciate your time.
You're welcome. It's my pleasure.
Great. Thanks again.